Hello guys, now I read Modern Approach to Organic Chemistry is written by Dr. J.M. Sehgal. Now I read chapter 3 Dienes. Introduction. The alkali dienes, or as they are more commonly known, the dienes are unsaturated hydrocarbon containing two carbon-carbon double bond per molecule. They have the general formula CnH2n minus 2 and are isomeric with alkynes, but the behavior of dienes and alkynes is quite different from each other. Classification. Dienes are divided into three classes depending upon the arrangement of double bond in the molecule. The three classes are: first, isolated dienes. The dienes in which double bonds are separated by one more than one single bond are called isolated dienes. For example, 1,4-pentadiene, 1,5-hexadiene. Second, cumulated dienes. The dienes in which the two double bonds are present between successive carbon atoms are called cumulated dienes or allenes. For example, 1,2 propadiene or allene, 1,2 butadiene. 3. Conjugated dienes. The dienes in which the double bond are separated by a single bond are termed conjugated dienes. For example, 1,3-butadiene, 2,4-hexadiene. Nomenclature. Cumulated dienes are commonly named as alkyl derivatives of allene, which is the simplest member of this type of dienes. For example, methylallene, 1-ethyl 3-methylallene, 1,3-dimethylallene. IUPAC nomenclature of all type of dienes is similar to that of alkenes, except that the numerical di is added before the suffix "-ene" to indicate the preference of two double bond. For example, 1,2-propadiene, 1,3-butadiene, 1,3-butadiene, 5-methyl, 1,3-hexadiene. Relative stability of dienes. It is interesting to note that difference in the relative location of double bond in their molecules causes appreciable difference in the relative stabilities of different classes of dienes. The data on heats of hydrogenation of alkenes and dienes clearly show that conjugated dienes are more stable than the non-conjugated ones. For a diene, the total heat of hydrogenation may be accepted to be the sum of heats of the hydrogenation of individual double bond. This is found to be so for non-conjugated dienes. For instance, the observed heat of hydrogenation of 1,4-pentadiene is 254.4 kilojoule per mole, while the accepted value is 251 kilojoule mole per minus 1. But in case of conjugated dienes, the observed value are lesser than the anticipated value. For example, the actual heat of hydrogenation of 1,3-butadiene is 238.2 kilojoule per mole, which is 12.8 kilojoule lesser than the accepted value. Similarly, the heat of hydrogenation of 1,3-pentadiene is about 16.7 kilojoule lesser than the accepted value. Now, two isomeric dienes which differ only in the relative location of double bond. Example, 1,4-pentadiene and 1,3-pentadiene give rise to the same alkane on hydrogenation. Still, if the conjugated diene evolve lesser energy than the non-conjugated one, only means that the former contains lesser energy than the latter. In other words, conjugated diene system is more stable than non-conjugated diene system. The greater stability of conjugated dienes may be explained in terms of resonance or delocalization. 3.5 Structure of 1,3-butadiene. It has been stated above that conjugated dienes are more stable than non-conjugated dienes. The extra stability of conjugated dienes can be explained in terms of their structure as discussed below by considering the structure of 1,3-butadiene. 3.5.1 Resonance structure. Unlike non-conjugated dienes, conjugated dienes exist as resonance hybrids of various contributing structure. For instance, 1,3-butadiene is a resonance hybrid receiving contributions from many structures, the more important of which first structure, second structure, and third structure. It should be noted that structure 2 and 3 involve separation of charged particle. As such, structure 1, which does not involve any separation of charge, is the most stable and therefore the most important of all the contributing structure. The actual structure of 1,3-butadiene is a resonance hybrid which lies somewhere in between the contributing structure but resemble that structure one more is closely. This means that the bond between one carbon and second carbon or third carbon and fourth carbon is not a pure double bond but quite close to it. Similarly, the bond between second carbon and third carbon in between a single and double bond but near to a single bond. This is in keeping with the fact that bond length between first carbon and second carbon or third carbon and fourth carbon is nearly the same as that of a double bond, while the bond length between second carbon and third carbon is somewhat lesser than that of a single bond, thus the relative greater stability of butadiene can be attributed to resonance, thus resonance energy being 14.6 kilojoule per mole. A similar situation is responsible for the greater stability of other conjugated dienes as well. 3.5.2 Orbital structure. The orbital picture of conjugated diene affords a better way of understanding the nature of bonds in conjugated dienes. For this purpose, let us again consider 1,3-butadiene as a typical case. Each of the four carbon of 1,3-butadiene uses their sp2 hybrid orbital for the formation of pi bond and an unhybridized p orbital for the formation of pi bond. A. Show p orbital of the four carbon atoms of butadiene before the formation of pi bond. Overlapping of p orbital of carbon first with that of second carbon and of the p orbital of third carbon and fourth carbon is shown in figure B. However, if the four carbon and the hydrogen attached to them lie in the same plane, then the p orbital of first carbon and second carbon can also overlap as depicted in figure 3.1. C. This means that there is an overlapping of p orbital of first carbon with second carbon with third carbon, and third carbon with fourth carbon as shown in figure 3.1d. This results in the formation of a pi molecular orbital which overlap all the four carbon atom. Figure 3.2e. As already explained, such a molecular orbital which is spread over the nuclei of more than two atoms is known as delocalized molecular orbital, and the electron present in it are termed delocalized electron. As in case of normal or localized molecular orbital, delocalized molecular orbital also consists of two electron cloud, one lying above the plane of atom and the other lying below it. Figure 3.1e. The presence of delocalized orbital is supported by the fact that the bond lengths between any two adjacent carbon atom in 1,3-butadiene neither correspond to carbon-carbon single bond length nor carbon-carbon double bond length. First figure p orbital of the 4 carbon of 1,3-butadiene before the formation of pi bond. B figure. Overlap of p orbital of one carbon and with the second carbon and third carbon and fourth carbon. C. Overlap of p orbital of second carbon and third carbon. D. Overlap of p orbital of one carbon and with second carbon with third carbon and third carbon with fourth carbon. E. Delocalized pi molecule orbital of 1,3-butadiene. Thus, the greater stability of 1,3-butadiene is used to the presence of delocalized electron, as such pair of delocalized electron attract and is attracted by 4 and no 2 nuclei. Method of formation of dienes. Dienes are generally produced by suitable variation of the method employed for the preparation of simple alkenes. The more commonly employed methods are given below. First, catalytic dehydrogenation of alkane or alkene. For example, 1,3-butadiene may be prepared by passing the vapor of N-butane over heated Cr2O3 Al2O3 catalyst. 1,3-butadiene is also obtained by passing the vapor of 1-butane or 2-butene over heated nickel phosphate or calcium phosphate. Second, dehydrohalogenation of dihalogen derivatives. For example, on heating with alcoholic potassium hydroxide, 1,3-dichloro-3-methylbutane give isopropene. 3. Dehydration of diols in the presence of acid. For example, dehydration of 1,3-butadiol by heating in the presence of a sulfuric acid or phosphoric acid result in the formation of 1,3-butadiene. 4. Pyrolysis of cycloalkene. For example, 1,3-butadiene can be prepared by passing the vapor of cyclohexane over heated nichrome, an alloy of nickel, chromium, and iron. 3.7. Chemical reaction of dienes. The chemical properties of dienes are essentially due to the presence of two carbon-carbon double bond in their molecules. Thus, non-conjugated dienes behave in exactly the same manner as simple alkenes, except that the attacking reagent is consumed in twice the amount required for one double bond. In case of conjugated dienes, however, the properties of the double bond are considerably modified due to the characteristic relative arrangement of double bond. This relative arrangement molecule enables the this relative arrangement enables the two double bond to interact with each other so as to modify the behavior of the molecule as well. Thus, conjugated dienes are characterized by their greater stability and the occurrence of 1,4 addition reaction. The important reactions of dienes are discussed below to illustrate their behavior. 3.7.1 Electrophilic addition reaction 1, 2 and 1,4 addition reaction. Dienes undergoes the usual electrophilic addition reaction shown by alkenes. However, due to the presence of double bond in the molecule of dienes, the total quantity of addendum is naturally 2 times the required for an alkene. The most electrophilic addition reactions are given below. First, addition of halogens. When treated with halogens, dienes react with 2 moles of halogen per mole of diene to form tetrahalogen derivatives. For example, 1,3-butadiene, 1,2,3,4 tetrabromobutane. The really interesting point, however, is what happens when only 1 mole of the addendum is made to react with 1 mole of the diene. In such a case, the two double bond in non-conjugated diene act independently of each other and addition take place across there of the double bond. For example, 1,4-pentadiene, 4,5-dibromo, 1 pentane. but a different situation prevails in case of conjugated dienes. To illustrate it, let us consider the addition of 1 mole of bromine to 1,3-butadiene. The product obtained consists of a mixture of 3,4-dibromo-1-butene and 1,4-dibromo-2-butene as shown below. The formation of 3-bromo-1-butene is not surprising as it is a result of normal addition to adjacent carbon atom liked by a double bond, but the formation of a 1,4-dibromo-2-butene due to 1,4 addition appears to be unaccepted. Mechanism of 1 2 and 1 4 addition to conjugated dienes. To understand the occurrence of 1 2 and 1 4 addition reaction, let us examine the mechanism of addition of bromine to 1,3-butadiene. The reaction takes place in two steps through the initial formation of alkyl carbocation. First, formation of carbocation. As the bromine molecules approach the diene and gets polarized, the positively polarized bromine adds to C1 to O butadiene to form an alkylic carbocation A and a negative bromide ion. A primary carbocation should also be formed by the initial addition of bromine to carbon 2, but the ion A is formed in preference to this primary carbocation, as former is not only a secondary but also an alkylic cation which is stabilized by resonance between structure A and B. The two contributing structure A and B differ from each other in the location of double bond and of the positive charge. In the resonance hybrid of these structures, the positive charge is not localized on carbon 2 or carbon 4 but is spread over both as shown below. Second, addition of bromide ion. It is clear that there are two positive charge centers in the cation which may be attacked by negative bromide ion in the second step of addition. Addition of bromide ion at C2 would give 1 to addition product, while addition of bromide ion at carbon 4 would have 1 for addition product. Third, addition of halogen acids. Addition of halogen acids to conjugated dienes is similar to the addition of halogens. Addition of 1 mole of halogen acid to a conjugated dienes gives rise to both 1 2 and 1 4 addition product. For example, mechanism to start the reaction: a butadiene molecules abstract a hydrogen ion from hydrogen chloride to form an alkylic carbocation and a negative chloride ion. Initially, addition of hydrogen ion could also take place at C to give a primary carbocation CH2 double bond CH single bond CH2 single CH2 positive. But the ion C is formed in preference to this primary carbocation, as the former is not only a secondary but also an alkylic cation which is stabilized by resonance between carbon structure C and D. Structure, structure C is CH2 double bond CH single bond C positive H single bond CH3. Structure D, C positive H2 single bond CH double bond CH single bond CH3. The resonance hybrid of these contributing structure may be represented as shown below. Thus, there are two positive centers which may be attacked by negative chloride ion in the second step of addition. Addition of chloride ion at carbon carbon second would give 3 chloro 1 butane, while addition at carbon 4 should give 1 chloro 2 butane. 3.7.2 Effect of temperature on 1 2 and 1 for addition to conjugated dienes. It has been found that the ratio in which the 1 2 and 1 4 addition product are formed in a result of electrophilic addition to conjugated dienes is largely governed by temperature at which the addition reaction is carried out. Generally speaking, Generally speaking, 1 to addition product is formed preferentially at lower temperature, while 1,4 addition product predominates at higher temperature. For example, 1,3-butadiene is heated 193 Kelvin. Now we product 1,3 adducted 80% plus 1,4 adducted 20% of CH3 single bond CH double bond CH single bond CH2 Br. Explanation of effect of temperature on 1,2 and 1,4 addition. The effect of temperature on 1,2 and 1,4 addition reaction may be attributed to the following reaction. First, E act leading to 1,2 addition product is less than that leading to 1,4 addition product. As such, 1,2 addition take place more readily than 1,4 addition. However, 1,4 adduct once formed as more stable than 1,2 adduct. Second, both the addition product can undergo ionization formation a common carbocation first. This leads to an equilibrium between the two products and the carbocation as shown below. Since the energy difference between 1,2 adduct and carbocation first is lesser than between 1,4 adduct and the carbocation, ionization of 1,2 adduct take place readily while that of 1,4 adduct take place slowly. At lower temperature, ionization of products occur to a very small extent only so that the 1,2 adduct which is formed faster is the main product isolated. This means that at lower temperature the relative amount of the two products obtained are in accordance with their relative rates of formation. In other words, the reaction is kinetically controlled. At high temperature, ionization becomes more important. The 1,2 adduct, which is thermodynamically less stable, readily ionize, while the 1,4 adduct, although formed slowly, does not ionize readily. As such, the 1,4 adduct is present in large quantities when the equilibrium is reached, and therefore is the main product obtained. In other words, at high temperature, the reaction is thermodynamically controlled. Second, free radical addition reaction. Like simple alkene, conjugated dienes also undergo contain free radical addition reaction in presence of suitable organic peroxides. Moreover, addition of free radical can again lead to the formation of both 1,2 and 1,4 addition product. For example, mechanism. The mechanism of free radical addition, such as that gives above, may be summarized as follows. First, peroxides red. Red plus BRC chlorine 3. Red single bond Br plus C radical chlorine 3. It may be noted that the alkyl free radical formed in step 3 is a resonance hybrid of structures E and F. In the resonance hybrid, the odd electron is distributed between carbon second and carbon fourth. As a result, this alkyl free radical can form either 1,2 or 1,4 addition product by abstracting a bromine atom from another molecule of BrCCl3. The newly bromide CCl3 radical then carries on the chain process. It is interesting to note that the free radical addition to conjugated dienes proceeds at a much faster rate than similar reaction with the simple alkenes, even though the conjugated dienes are themselves more stable than simple alkene. This unaccepted reactivity of conjugated dienes towards free radical addition is attributed to the much greater stability of intermediate allyl free radical as compared with the intermediate free radical formed from simple alkenes. Therefore, the net E act for the formation intermediate free radical formed from simple alkenes. Therefore, the net E act for the formation of intermediate allyl free radical is lesser than E act for the formation of intermediate free radical in case of simple alkenes. As such, the free radical addition to dienes take place more readily and at a faster rate. 3. Diels elder reaction 4 plus 2 cycloaddition. This is one of the most important reaction of conjugated dienes. It involves an addition reaction between a conjugated diene and a compound containing a double bond called a dienophile. Diene loving to form a six-membered ring since the reaction involves the addition of a 4 pi electron system to a 2 pi electron system and leads to the formation of a cyclic product. It is often referred to as 4 plus 2 cycloaddition reaction. The product formed is often called a Diels elder adduct. The simplest example of Diels elder reaction is that between 1,3-butadiene and ethylene, but the reaction takes place very slowly and in low yields 20%. 1,3-butadiene plus ethylene at 473 Kelvin product is cyclohexane. The reaction takes place by a concerted single step mechanism during which carbon first and carbon 4 of the conjugated diene system get attached to the doubly bonded carbon of the dienophile. As a result, two new sigma bond are formed at the cost of 2 pi bond of the diene and dienophile, as is clear from the above example. Diels elder reaction take place very readily when substituted alkenes containing electron withdrawing group are used as dienophiles. For example, first, the reaction between 1,3-butadiene and acrolein take place 373 Kelvin to form the adduct in quantitative yield. Second, maleic anhydride react readily with 1,3-butadiene at room temperature to give quantitative yield of the adduct. Factor which favor the reaction. It was originally stated by Elder that the reaction is favored by the following factor. First, presence of electron withdrawing group in the dienophile. The favorable effect of the electron withdrawing group in the dienophile is very clear from the example given above. It has been seen that acrolein and maleic anhydride undergo Diels elder reaction in quantitative yield even under mild condition. Second, presence of electron releasing group in the diene 2,3-dimethyl 1,3-butadiene affords and important example of a diene to demonstrate the favorable effect of electron releasing group in the diene. This compound contains 2-methyl group is about 5 times more reactive in Diels elder reaction than 1,3-butadiene. For example, 2,3-dimethyl 1,3-butadiene react with acrolein in quantitative yield at only 303 K. At against this, 1,3-butadiene react with acrolein in quantitative yield only at 373 K. Stereochemistry of Diels elder reaction. The elder reaction is highly stereospecific. The important aspects of its stereochemistry are as follows. First, as cis in conformation of diene. The diene undergoing the reaction must be in the S cis formation rather than S trans conformation. This is because only the S cis conformation allows the end of the conjugated system to reach the doubly bonded carbon of the dienophile. S cis conformation necessary for Diels elder reaction. Reversible reaction as trans conformation. Third, occurrence of Shine addition. The reaction takes place by sign addition of the diene to the diphenol, and the conjugated of the dienophile is retained in adduct as illustrated. 1,3-butadiene plus dimethyl methylates product dimethyl cis 4-cyclohexane 1,2 dicarboxylate. Synthetic utility of dienes alder reaction. The synthetic utility of the reaction lie in the fact that it can be used in the prepar- preparation of a many cyclic compound which would be difficult to prepare by other means. A prominent feature of the reaction is that it is extremely easy to carry out. In most cases, the reaction is brought about by merely heating the reactants together with or without a solvent. 4. Polymerization reaction. Conjugated dienes have a strong tendency to undergo free radical polymerization to form useful high molecular weight polymers. First, polymerization of 1,3-butadiene peroxide. Induced polymerization of 1,3-butadiene gives rise to polybutadiene. 1,3-butadiene peroxide polybutadiene. The formation of polybutadiene involves predominantly one for free radical addition of butadiene units to each other so that the product obtained still contain a double bond for each butadiene unit. Second, polymerization of 2-methyl-1,3-butadiene. The free radical polymerization of 2-methyl-1,3-butadiene or isopropene gives polyisopropene which resemble natural rubber. Thank you so much.